Section 25.1 is about the nucleus. We've talked about the models of the atom. Now we're going to zoom in on the nucleus. We're going to forget about the electrons for a little while. Let's go to the first slide. First, we've got three things that make up the nucleons. Nucleons are subatomic particles. Sorry, two things. Three definitions. Two things. Protons and neutrons. Yeah, this should be a review, this first slide. I really hope it is. You guys need to stop talking. Stop. Thank you. The atomic number is listed as Z. And Stop talking. Stop talking. And the atomic number is the number of protons. Always, 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 always. Okay? So we know the number of protons is Z. The number of neutrons is N. Okay, this is the neutron number. Now, what do you know about any atoms? What makes up the mass of an atom? The nucleus, and only the nucleus. The electrons are considered negligible. So what can we say is the atomic mass equal to? Elliot? Yeah, both neutrons and protons. Protons and neutrons both weigh about the same mass, or both mass the same. Neutrons really only have the extra mass of what would be an electron, which is considered to be negligible. So we have neutrons and protons summing together to give us the mass number. A question was posed in the last class that they had a tendency to see the mass number on the bottom sometimes on the top. Doesn't matter where it is. The mass number is always going to be bigger than the atomic number. Think about it logically. For any element on the table, you're going to have protons as the atomic number, and then the mass number is whatever the protons were, plus the neutrons. So if it's got any neutrons, that mass number has got to be bigger. So the bigger of the two, in this case for aluminum, 27, is the mass number. 13 is its atomic number, or the number of protons. So how many neutrons are there in aluminum? Not 13. 14. Because we have 13 protons plus another 14 neutrons give us 27 as a mass number. Okay? So in this example on the right, since there are 13 protons, there have got to be 14 neutrons to give us a total mass of 27. Any questions? Any questions? So let's take a look at the amount of protons versus neutrons. So each element has a specific amount of protons, which dictates its atomic number. For example, what's carbon's atomic number? What is it? 6. Carbon is 6. What's its mass? 12. Okay? But you know what? I've heard of carbon-14. What's that? It's an isotope. An isotope is another form of that atom that occurs with a different amount of neutrons. So, we say that the amount of neutrons in a given element can vary. And we call these atoms that have different number of neutrons isotopes, as we said. Okay, isotopes. So carbon-6, 12. Carbon-6, 14. Are there others?
18.
Carbon?
17.
Are you sure you guys are saying numbers right now?
I think 18 carbon 6.
Can somebody just type in carbon isotopes?
Carbon 11.
Are you just saying that? Okay. Of carbon, there's 15 of them?
Yeah.
Oh, geez. All right, so let's hypothetically say that. I'm going to put some random ones out there.
Carbon 11 is one.
Yeah, it is. Carbon 11, carbon 12, carbon 13, carbon 14.
11, 12, 14, 15, 16?
17, 18, 19, 20, 21, 22.
All right, so let's say there's a bunch of them, right? When you look on the periodic table, you know that you actually see, you don't see carbon-6, 12. What does the periodic table show? Anybody know? This is the most naturally occurring.
Simplest state. Simplest form.
That's what it shows. It shows carbon 12.01. What the heck is that all about? How did we get 12.01? Come on, guys, you did this last year in chem. If I tell you, I think you're going to be like, ah, that's what it is. Which of these carbon isotopes occurs the most? What did I say?
12.
Carbon 12 occurs the most.
And that is 12. In its natural form.
They just like, it's 12.01, but then they said 12.
Where's the .01 come from? You know where it comes from?
Is it like the rest of them, like the average?
Yes, it's the average of all the carbons that exist. So imagine that 90% of carbon that exists is carbon 612. Then there's like 5% carbon 614, 1% carbon 615, and then only fractions of percentages of the others. If you took all the carbon elements on the Earth, extrapolated it, added them all up, all the masses, and divided by however many there are, you get 12.01. This is a weighted average. The atomic mass that you see on the periodic table with a decimal value there is a weighted average. Okay? It's a weighted average. Do you remember this from chemistry? Seriously? I'm almost positive you did it because I was teaching a math lesson and Mr. Joseph was talking about the same thing. He's like, oh yeah, we talk about weighted average when we come up with the atomic mass in chem. And that's what made me think of this. Because I was doing weighted averages in my math class. All right. Oops. The density of a nucleus. The density of a nucleus. First of all, let's use carbon 612 as another example. So let's draw 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to just draw a random orientation of 6 protons and 6 neutrons. Okay, so we'll say that this is carbon right here. Now, obviously, this is in a circular or spherical shape, but I'm clearly not drawing a good representation of that, and it's in 2 dimensions.
I think that's good.
Okay, thanks, Mike. Appreciate that. So, if you want to slide up to the previous slide, I think I have an image of a nucleus, correct?
Yeah.
So, look at the image on the previous slide of a nucleus, and image or visualize that while you see this. Now, what happens is the nuclei, they're pretty much spherical, and the protons and the neutrons are about the same mass, right? We said they're both about 1 unit of mass, 1 atomic mass unit. That's where we get 12.
There's one actually
Add up
heavier,
all.
though.
What's that?
There's one actually heavier.
Well, yeah, the neutron is heavier by a small amount of pretty much the difference between that and an electron. It's got an additional electron in it. But electrons' masses are negligible, so we say they're the same. But theoretically, they're the same mass, okay? Now, if that is true about this, then what can we say as the atoms get bigger and bigger and bigger about their density? This is a little bit tricky. So imagine now you have oxygen.
Wait, did you say they were empty?
No. I said, what happens to the density even as we increase in number of atoms? So this is way out of scale. That was stupid of me. That was really stupid. So this should be larger on the right than on the left. I don't know what I was doing.
Wait.
Nick, what was your statement going to be? Decrease in density. Mike, you said less dense. Which you would think, and I don't know why I drew it this way, which doesn't matter. If they have the same mass, imagine taking, ready? A bucket of water. You fill it halfway. Okay? If I fill it with another half-filled bucket of water, so I make up the difference, I'm putting in the same mass that was in there. Agreed? Is the density changing? So if I have 1 part water, and I double that amount of water by putting the same amount in, the density does not change. It's still water, right? So I'm not changing anything. I'm just putting more of the same exact mass in. So the volume's getting bigger because I'm putting more mass in. And that's why I said this was not drawn to scale. So can I erase this? Yeah. If I had oxygen, or let's say carbon. It does not look like that, but I'm just trying to draw quick. And oxygen. Okay, and this makes more sense now, right? This is a smaller volume than the second volume. The volume is increasing Because there's more mass, and they're the same mass. They're all the same shape. They're all spherical. So the volume is increasing, but so is the mass. Okay, this is M1, and this is M2. What is density defined as? What is density defined as? Mass over volume. And in physics, we write density, and you'll see this in the next chapter. So I'm going to write it this way now, as like a P. It's a little swirly. You actually start like this, if you want to look up. This is how you draw it. Okay? Or like this. It's an exaggeration. But it's called rho. R-H-O. Okay, rho. Like you pronounce it like row your boat, but spelled R-H-O. So density equals mass over volume. If the mass goes up and the volume goes up, it turns out that the density is pretty much the same for all nuclei. So it doesn't matter what size nucleus it is. The density is approximately the same for all nuclei, which is pretty amazing to think about that. The density does not change for any of them. That density, and this is going to be an incredible value when I tell you what it is relative to a number you know. 2.3 times 10 to the 17 kilograms per cubic meter. That is, ready? 230 trillion times more dense than water. Water's not super dense, obviously, but it does weigh a decent amount. Imagine something that weighed, you held a bucket of water, right? Now multiply the weight of that by 230 trillion. That's the density of a nucleus. 230 trillion times that of water. So the weight of water would weigh, or of a nucleus, would weigh 230 trillion times if you had as many nuclei to fill up a bucket of water. Very nice, that's cool. Maria drew a three-dimensional version of what I was trying to draw. Like any of these values? No, I mean they've been tested and proved. That's the whole idea. It's not a theory anymore. The masses can actually be massed. Yeah, which is pretty incredible to think about.
That's not like the weight of it. That's just...
The density is constant, and the density is 230 trillion times more than water. So if you had a bucket of nuclei and a bucket of water, the bucket of nuclei would also weigh 230 trillion times more. 230 trillion times.
The water has nuclei in it.
Huh?
Water has nuclei in it, though.
Sure it does, but most of the atom is empty space, remember? The nucleus is very dense. You can't have a bucket of nuclei because you can't get that many nuclei by themselves. You always get atoms, and atoms are mainly empty space. So the overall density of an atom is actually quite low, while the density of the nuclei is extremely large.
So technically a bucket of nuclei would be impossible to pick up.
Of course, a bucket of nuclei would fall through the Earth's surface. Their surface would not be able to withstand its weight.
I could pick it up.
What?
No, you couldn't.
I
Maybe Goku at Super Saiyan level like 100.
I guarantee I
Do you watch anime in your free time?
No, but I did watch Dragon Ball Z.
You watch anime in your free time?
Only Dragon Ball Z is the only one I've ever seen. It's good. Alright, nuclear stability. Nuclear stability. Hey, think about this for a second. What is in the nucleus? Please listen, folks. What is in the nucleus? Protons and neutrons. The atom is mainly empty space. What's in the nucleus is protons and neutrons. Now, what does that mean about the charge of a nucleus overall?
Not positive.
It's dominant positive. Because a neutron is what?
Protons and...
Neutral. Here's a neutron. Here's a neutron.
Wait, what do you mean?
Proton.
Positive?
Proton.
It's always positive. Wait, unless there's more neutrons than...
No, then it would still be.
Wait, is it possible for an only type of neutron and not a proton? Like for a nucleus, just have a neutron?
But you could split a nucleus apart into its components of neutrons and protons. Okay? So you could break up an alpha particle, which is really two neutrons and two protons together. There's also, I think, a beta particle is a neutron and a proton. It's a hydrogen proton, with an additional neutron, I think. I'm pretty sure. That's what I think.
Wait, what happened? Can the
Is
number
it a
of
beta
neutrons?
particle?
Can the number of neutrons outnumber the number of protons?
Yes, and that's what we're going to talk about, Mike. Really good to see that. All right. So think about this for a second. Everybody, look up. Look at all this positive charge. What do we say about like charges? Like charges repel. So do they want to stay next to each other? So what's binding this nucleus together? The strong nuclear force. It was called the strong force for a long time because it was the strongest of the forces. It was stronger than the electromagnetic force that's pushing them apart. Okay? But then, later on, there was another force that was discovered. Okay? Believe it or not, that was called the weak force. So this is also known as the nuclear force, which I tend to call it, because it doesn't make sense to call it the strong force when it's not the strongest force. Okay? But the idea is this. The strong force only works on a small scale. So these protons right here, they're really close to each other, right? But what if I had an element like uranium-238? Now you have 238 protons and a lot of neutrons, a whole lot. So how far apart are those protons now?
Really far.
They're really far. So imagine a proton out here. Imagine I filled in all this space with protons and electrons, and there's a proton all the way out there. Now, the force of electric repulsion between these two protons exists. But the force of attraction, the strong force, or the nuclear force at this distance does not really exist. It's zero. Okay, it does not really exist. It is negligible because they're too far apart. So when elements get bigger and bigger and bigger, suddenly you have this repelling force pushing them apart. And the strong force isn't there to help. The strong force is here, but it's only here. There's the strong force there between these two protons, and maybe between these two protons, and between these two protons. But when they get too far apart, the strong force doesn't happen anymore. And now all you have is this abundance of repulsive forces. So what happens is, when you have heavy nuclei, and the number of protons is more than the number of neutrons, you get this repulsion of electric force. And what does the nucleus want to do?
Find something to hook up on.
Yeah, spread apart or go attach onto something else.
What am I thinking?
So you have what kind of decay?
Exponential.
Exponential, it is exponential decay. Uranium. Radioactive decay. We're going to talk about fission and the separating of a molecule and atoms. Okay, but this is radioactive decay. So what you can say is the following. Okay? Is that for an atom to be stable, you want the number of neutrons to be bigger than the number of protons. Because the number of neutrons, if you have a lot of neutrons, watch what happens. Right here, there's strong force between that neutron and proton. Right here, there's strong force. Right here, there's strong force. Strong force. Strong force. There's so much strong force. There's strong force between every single linking value here that's close. All of these have strong force between them when they're close to each other. But between the neutrons, there's no electric force. So if you have more neutrons, then you've got a lot of strong force keeping it together. But if you have a lot of protons, then you have a lot of electric force pushing it apart. So you really want to have, again, you want to have more neutrons than protons. The number of neutrons N wants to exceed the number of protons Z to have stable, large atoms. This is for large atoms. For small atoms, they are stable the way they occur because they're so close. Think about a helium atom. They're so close, those two protons and those two neutrons, that the strong force supersedes the electric force. So a helium atom is naturally occurring to be stable. Whereas when you get to uranium and stuff, you need to have more neutrons. So you have more strong force, and it overcomes that electric force of repulsion. Okay? Again, the strong force only works well when it's really close up, when it's at a close proximity. Okay, that's why smaller atoms are more stable. Smaller atoms are more stable. All right, that's it for today. That's the whole idea. What questions might you have? We've got a few minutes real quick.
Wait, but like
About 10 minutes. What questions, Mike?
What happens if there's more, like, what happens if it's unstable? Like, working out? Does it just, like, fall apart?
It starts to decay, and alpha particles and beta particles start to get shot off in form of radiation. And that's radioactive decay. Remember how, what was her name? Marie Curie? She studied radioactive isotopes, remember? She died early because of all the radioactive decay and all the radiation she was getting from that. So cancer treatment, a lot of cancer treatment, they'll send radiation into the body to help you to fight off the cancer cells. It kills them. It's specific types of particles. But it also has a tendency to kill some good particles, which is the debate when you get radiation. But it extends your lifespan. The goal, obviously, is to have some sort of radiation treatment that can specify to only kill the cancer cells and not the good cells. So what researchers and genetic engineers and radiologists try to do is to try to come up with treatments that really only kill cancerous cells. That's where you get things like trackers now. That's why nanotechnology is so important. If you could work at things on a nanoscale, smaller than a simple atom, you could then specifically target certain cells and work on just those cells. That's why this treatment and these ideas of constantly putting money into science and research is so important. Okay? Because of reasons like this. It's a really good application of it. But that's what's happening when you get chemotherapy. It's a radiation treatment. Okay? What other questions may you have on this topic? Make sense? Yeah? Reese?
I don't get the nucleus thing about if it's dense, if it's so super dense, that means it's really heavy. Right? Okay, so if it's so heavy, then how come, like, how do get the water thing? Because water has atoms, obviously, and in the atoms there are nuclei.
Well, what I was trying to say was this. It is misleading to get more massive. Think about it. If I've got a bucket of water, or a cup of water, it weighs a certain amount, or has a certain amount of mass. If I put more water in, isn't it getting more massive? There's more mass getting put in.
Yeah.
But is the density changing? It's water still.
Yeah.
So what's the density of water? 1 gram per cubic centimeter, just 1. It's our most fundamental density. So the density of the water, even though I'm adding more mass, is still 1, right? So if I keep adding more protons and neutrons to the nucleus, making it a bigger nucleus or studying larger atoms, the nucleus is still the same density. It's just getting larger. So that was just one of our theories, or one of our, not theories, one of our statements.
If it's the same density, it's still equally as heavy.
It's not, no. You're confusing weight, mass, and density. Mass is the amount of matter. Weight is that amount of matter times the gravitational pull. Density is that amount of matter over the volume it takes up. They're all 3 different things. Okay? So if I add more water, I'm making it more massive, and as a result, there is more weight. Agreed?
Yeah.
But the density is still the same.
Yeah.
It's still water. Water is, and the density is a material property. It doesn't change if you have more of that material. If I have a pane of glass with a given density, and then I have a thicker pane of glass, but it's the same glass, the density is the same still. The mass is increased, the thickness is increased, the weight of the window is increased. It's a heavier window to lift up, but the density of that material, it's still the same, it's still glass. Density is a material property. It's part of the atomic structure. Okay? So what I want to indicate is this. If you have more protons and more neutrons, isn't it the same thing still? It's more massive, it's got more weight, but its density is still the same. So every nucleus, no matter what size, has the same density. Because it's still just a composition of protons and neutrons. It's made up of only protons and only neutrons, so the density is constant for all atoms. Okay? Good? Other questions right now? We got 5 minutes still. We can pause.